Okay, so I hope you can hear me. Let me share the screen. So, okay, so let us start today with the chapter. I think we stopped at that point last time. This is about different types of architectures of data platforms. Last week, we discussed in general the non-functional requirements that the data platform should fulfill. These are, of course, quite similar to NFR's non-functional requirements that other applications in the business context need to fulfill. But nevertheless, of course, questions about data quality and so on are in data platforms of particular relevance. So the next thing now is to discuss a little bit about the, let's say, basic architecture or general concept that such a data platform can follow. And first of all, we have basically two basic variants, which is batch and stream processing. And then we will see how these can be combined in the Lambda and Kappa architectures. So let's start with batch processing. So batch processing is let's say, the most traditional form of computer usage. In the early days of computers, in the 50s and 60s, there was only batch processing. The original name batch is actually denoting the batch, the physical batch of the punch cards that were used to feed a computer. So the early computers, they had an input, which basically was kind of a tray where you put in the punch cards, which was called the punch card reader, and you could just put one stack of cards, one batch above the other one, and at the bottom there will always be the first card would be read by the computer. And so a program consisted of a batch of cards, or the data that the program was processing consisted of a batch of cards, and the system just read in this, processed it, and output the result either by punching a new set of cards for further processing, or by printing, for example, on paper or something like that. So that was the way how computers worked in the early days. So the name batch for having a batch of tasks or a batch of data remained, and today we denote with batch processing the typical way where a computer gets a task description, a job, like a script or something, that the computer then runs, and these jobs are executed simultaneously. So we can have multiple tasks in parallel, and of course, one job is run after the other one. So that this old paradigm of the punch card batch is actually kept, but of course today it's software. It's written in files or a disk or so on. The advantage of that is that in this kind of operating model, where you actually give the computer a task and the computer processes it asynchronously, one after another, at some not exactly defined point in time after you submitted it, and all the tasks that come in are queued in a queue, and the computer always reads the first task. This has the advantage, of course, that the computer cannot be overloaded, because you always know how many parallel executions happen, and that you can also tune it very efficiently to actually have the full load used of a computer. If you have enough work to do, you can just run as many parallel tasks until CPU and memory are more or less always busy. So you can make the best use out of your hardware. This is the reason why, for example, in high performance computing or supercomputing, where you really have these expensive high performance computers, typically all these large scale calculations like training, for example, if you train an AI model, or you do some simulations or solve some large systems of equations or whatever, or these numerical computations on high performance computing, they are typically carried out in a batch model because they usually don't require interaction. You just have a pile of data, you have a program, then you train, just as an example. And so there's no user interaction. There's no need to wait for some feedback or something. You just put it in and let it run, and some point in the future it's finished. So that's a typical paradigm for compute intensive work with a lot of data and so on. So in many cases, it's not necessary to have kind of a online or real time or near time reaction or output. So the batch is very efficient. On the other hand, of course, there's no exact guarantee when you will get a result. So if it's something that is more interactive or requires the user wants to get a feedback or something, then of course batch processing is not the ideal. But for tasks that are more background work, this is really, really nice. So in general, you have kind of in a batch system, you have tasks or jobs that are executed, and you might have nets of jobs. So each job might trigger other jobs when it's finished. And also they have exceptions, so something might happen if a job runs in a problem or something during execution. And and you monitor the behavior of the jobs by, for example, by centralized management operating that looks, okay, is there some unusual delay? Or you also have maybe automatic surveillance where if a job takes much longer than expected, something will be happen or someone will be alerted or something like that. And batch processing is used in various kinds. So one typical usage is kind of the overnight or background processing in large enterprise systems where it is quite standard. And also in this data platform for kind of asynchronous tasks that are not required to be finished early, but can happen in the background. So as I said, it's very efficient. So you get more speed at a lower cost. You have not the need to be looking at the program all the time. And it's quite simple. So this is also because historically it was the easiest way to use computers. The the downside is, okay, debugging might be complex because you don't have really easy access to the system. And if something happens, it's not so easy to debug because you might not be able to run the program directly without having a lot of dependencies. And of course it's more it's a separate different kind of computing that might require additional efforts and stuff and so on. So the typical advantage is when you use batch processing, when real-time or near-time information is not needed. So it's not important that you get immediate feedback. Like, for example, when you train a large model, which is it's unsupervised learning. If you train an LLM, just have the data and you need the computing power and that's the system run. Or if you, for example, calculate if you mine a Bitcoin or something, can happen in the background. Or if you train or solve systems of equation, if you do climate simulations or finite element simulations or whatever, then this is something that can run in the background. Typically, you have large volumes of data, the data is there. That's also something. You do not have a continuous flow of data, but you have a big pile of data, a database or file or whatever, and that you process. And yeah, when you have some large work, for example, you work on a full table and join things, and the work is typically something that has to be redone frequently. So that is typical for batch in general, batch processing, which is one paradigm that might be useful for certain kinds of data processing platforms, especially in the context of AI. And the other is stream processing. Yeah, so that's basically the opposite. So in stream processing, you have a paradigm where the system continuously collects data and processes it on the fly. Yeah? So it's not that you have a pile of data, then you process it and you have a pile of output. But in this case, you have events coming in all the time, and they are more or less processed immediately, and also a result is processed or generated immediately. The advantage of that is that you can handle, of course, data that comes continuously and flows also maybe in a not which might be too large to store. Yeah, so you have, if you think of a camera or some sensors that continuously produce measurements or images or something, and you want to immediately react on that. Yeah? And you want to always monitor that, so the event comes in, you look at it, and if something is happening, then you would react. So it's a high throughput and low latency processing that is required. Then stream processing is relevant. There are different kinds of streams. We will see that later when we talk about different technologies. So you have the stateless option, so that the processing of a single event only depends on the information that is contained in this event. Simple example, you have a surveillance camera, it sends you an image every second or something like that. And you always want to know, okay, is, for example, something suspicious on this image or not? And then you have a neural network trained that classifies the image in suspicious or not. And the image comes in, you make the inference on the neural network says suspicious or not, and then you have an output. Yeah? So this system doesn't have a memory, so it's stateless. Every image is independent. You don't need any further information to do something with this image to calculate the output. So it's a stateless stream. There's no inner state of the process. So every event or every processing depends only on the information delivered by a single event. And we have stateful streams where actually the stream itself keeps some kind of memory. So the handling of an event might depend on the input that have been processed before. So the whole system has a memory. So it's in that sense that, for example, if something suspicious is registered, the system keeps that state, and subsequent images are maybe ignored because we already have suspicion or whatever. So the system keeps an inner state, persistent state over multiple events. So this is, of course, a way that is good for continuous data, but so it's one possibility to handle data that is in principle unbound. Again, look at the camera. Yeah? So if you have a camera that sends you a picture frame every second or something, you don't know how. So there will be an infinite number of images coming over time, but you would always investigate only a fixed chunk. So you would maybe look at a single frame or at a certain sequence, let's say 10 or 20 or 100 or whatever, but you will divide the data into fixed size chunks and then process these. And yeah, then you have this data, this chunk accumulated in a time window, and you would then use some operations on it, like, for example, filtering, aggregation, and so on. Classification, as I said in my example, you can run neural networks on it or whatever. So a typical stream platform has some kind of stream engine that handles the stream. So you can imagine a single stream is like a queue, like a FIFO, first in, first out data structure. So the events come in, the system buffers the events, processes them, and then sends the output maybe to another queue or to another system that receives these messages. And during processing of the events, you can apply data analytics to them. You can apply transformations to the data. You can generate other data from the data, and so on. And to do so, of course, you need some persistent storage in the system. On one hand, to store the messages in the queues to keep the system don't lose anything, and on the other hand, of course, to store some business information as well. So stream processing, where you can divide the problem, so means that you divide a problem into multiple processors that have an input stream, do something, send the output to the next step, which is another processor. This is a very simple paradigm to distribute load. We talked about these scalability issues in the first lecture. When I showed you that we have these two paradigms, vertical versus horizontal scalability. And I said on the horizontal scalability, you have the problem that you have many, many small machines, comparable small machines that need to interact. And of course, one paradigm that scales nicely on such a system is this pipeline processing. So you have stream. The stream consists of multiple transformations or operations. Each is an independent program running on one of the computers, and they always send the message to the next one. Yeah? So that, of course, then is very efficient. And if they don't need a common joint database memory, then they can even, if they're stateless, this is even more scalable. So that can be a paradigm that performs nice on distributed horizontal scalable platforms in the cloud. The downside, of course, is that it gets very complex if you have many of these processors. The latency is somehow dependent, of course, on network throughput and so on. So it can vary. It's not. It's very crucial or very difficult to keep a certain guaranteed latency in such a system. You need to find ways how to handle processing errors. So you might have error queues where you send things to. If during processing a single data item or a chunk or a record or whatever, an error occurs or problem occurs, you need to keep track of that. But because these small processes just shift every event to the next one, what happens if something goes wrong with the record? So you need to kind of phase it out of the pipeline and keep it separately. So it's a little bit like such an architecture is like you're building these car factory or something where you have this typical industrial project where the car every step does just one thing, then the car is moved to the next station, someone else is doing another operation, and it moves to the next, so something like that. So this conveyor belt thing where you should put through so that's basically a similar thing. Here you have this pipeline, the event is processed, the event is passed to the next processor and to the next, and so on. And in between there's a buffer, which is kind of the conveyor belt. But if something goes wrong, if there's a problem, you have to take out the suspicious or malicious object to not block the work. That's very, very similar to what they do in a car factory. If there's a problem, if for example, in some step it takes longer than planned, this car will be shifted out of the process and handled separately by another lane. So stream processing is nice for things like, as I said, surveillance, fraud and anomaly detection. You have a real-time flow of data. Edge processing. You have analytics on a device, like for example on a intelligent edge device. So an edge device is a embedded system that is directly placed on together with a sensor somewhere, for example, a camera or a sensor that measures something, and you do immediate processing on the edge of the system. So not centralized infrastructure, but really located close to the measurement. And so you process the data before you pass it, for example, to a backend system. And in this case, of course, you have a stream, and you could process these things also on an edge device, like small one, so system on a chip computer or something like that. For a kind of real-time analytics, clickstream, and so on, monitoring of different activities, could be a network, could also be industrial monitoring, financial trading, log analysis, whatever, yeah, security monitoring, and so on. Every time where you'll need kind of where you have a continuous stream of information that needs to be processed in short or on near time. So if you compare this, we have these kind of two ways we have now learned. We have the batch processing alternative or the stream processing alternative. When to use one of these depends on your requirements. They are not, they have different strengths and weaknesses. Yeah? The batch processing is very good in processing large volumes in a background or offline fashion. So the data needs to be there. Yeah? So you have a pile of data, and then you process it, and then you have an output. But you need people that handle problems, because if something goes wrong, you need to look what was the reason and restart it and so on. On the stream processing side, you have the advantage that or the structure, you analyze a continuous stream. The size or the number of events in the stream can be continuous, so you don't need to store them at once in one place. But on the other hand, you need to process the data roughly at the same speed as it's coming in, otherwise it will accumulate in the input queue. So the system has, like always, it's like a pipe. Yeah, what you put in, it comes out. So it's like if you have a water pipe and you put in too much water on the edge, then the water will get stuck there, or you will have water on the we have an overflow, basically. So you need to have a pipeline that is capable of handling the volume. So we have these two basic paradigms. Then they are kind of used in many situations. You have this batch, which is asynchronous. So you put the data on a big pile, submit a job, the computer will start this job at one point in time that you cannot really influence, and then it will be processed until it's finished. Stream processing, on the other hand, is continuous. It is real or near time, but of course, it's also crucial to have the infrastructure to actually process the data in the same speed as it is coming in. So that was kind of the two fundamental alternatives that you have. And now let's look at the Lambda and Kappa architectures. So the Lambda architecture is combines the two. Yeah? So it is a mixture or a blend of batch and real-time streaming processing techniques. And it implements, as we learned, we have these different steps of the data, or the different tasks that a data processing platform should fulfill. So you have ingestion, analysis, and memory, or keeping the data. And the Lambda architecture tries to combine the advantages of both paradigms, stream versus batch, and also to avoid the downside. No? So the Lambda architecture is the perfect choice for developing large data systems, because it can kind of balance the different properties. In general, the Lambda architecture to achieve this is made up of different layers. This batch layer, which is kind of provides the batch capability, streaming layer, which provides stream processing facilities, and a serving layer, which actually is there to collect the data and also serve it or deliver it, make it accessible to users or other systems. So you can think of that like this. Yeah, on the one hand, you have the input data coming in. It can be of different kind. Yeah? It can be files or piles of data, tables, as well as streaming. And it is actually processed in the batch layer, and then processed to the speed layer, and then we have the serving layer, which is used to present and analysis the data. Yeah? So this is kind of the user perspective. You have the data comes in, it's processed, it is aggregated and brought to the user in a centralized manner that it actually allows to analyze and work on it. So the functionality is like that. So the new data comes in, and we have then the batch and the streaming layers for processing it. The batch layer actually is there just to store the information and processing it to create views of batch data, whereas the streaming layer supports this by creating real-time views based on new and non-indexed real-time data. So it's a combination of the two. And so the goal is it tries to so the idea is that you have data, then you do some batch processing and put it into the service layer, and in parallel you can have also the stream layer handling kind of input that modifies then the batch data or augments the batch data. And this leads to these properties. You have a reduced latency, you have an improved scalability, because you have kind of the advantages of the batch processing. You can do the background work, and then the increment is handled in the streaming way. The downside is, of course, it's complex because it kind of does everything. Yeah? It combines two platform types, and you do rely on different technologies for the different tasks. And of course, you have different processing paradigms. So if you write a kind of a converter or some operation task or some code that actually does something with data, you basically need to do it in two ways. You need to have it in a batch manner and in a streaming manner to support both processing paradigms. So it increases the effort for the developer, for the users of the platform. And of course, it makes the whole thing more complex because it can do both. So again, this is, as you see, it's basically usable for all the tasks that we discussed. To compare, the other option would be the Kappa architecture. And the idea of the Kappa architecture is to reduce the complexity compared to the Lambda architecture. And it puts the focus on the actual streaming processing or stream processing. And this is achieved by so it handles everything as a stream. Yeah. Basically, you have the streaming layer and the serving layer, but we leave out the batch layer. Yeah. And so the focus is on the streaming side. And if you would have data that is of batch kind, you would kind of feed it into the streaming as well. You can take the file and then send it record-wise to the stream. So you would kind of treat everything as a stream. to avoid doing things in different ways. This is much simpler, of course, but of course has the downside that it cannot make use or use of the advantages of the batch processing in terms of resource consumption and efficiency and so on. So the Kappa architecture is like a Lambda architecture without the batch part, or with a reduced batch part. So here you see the comparison. The capability of the Kappa architecture is that you have, or the advantage is that you have reduced costly hardware, you have only one paradigm, and you would map everything to a stream, whereas the Lambda architecture would keep two different ways of processing things, data, depending on its nature. So if you want to train, for example, a large neural networks or models, AI models, you would probably prefer a Lambda architecture, because here you have the issue that you start with a lot of batch background work, for example. So here are some videos which you may use to also get a deeper understanding. And of course, here are some links. So that was the introduction to the platforms, to the theoretical concepts, and the basic types of architectures. And also last time we had this video, or you should have a look on the video on cloud computing. And as I said, okay, for many of these data platform tasks or building up a data platform, if you are a company and you want to build up a data platform, you typically will use cloud-based services for that. And of course, there are different ways to do it. And of course, we need to keep in mind the privacy and scalability issues and so on. So let's think of that. And to make you a little bit think more about that, we do an exercise now, which I will briefly sketch in the course and explain on the fly. So let's consider the following case. There's a company that wants to set up a data processing platform. And they want to use the Lambda architecture. So in general, it should be Lambda architecture. Lambda. They plan to do it themselves, so they don't want to use ready-made thing. They want to have a complete open source approach and a large goal is And it should be run on either cloud on-premise or virtual private cloud. And yeah, I think we have the most requirements. Those components should not run. Okay. And of course, we are they should not contradict the other requirements. Huh? So that is the goal. No? And now your task is so you should work out an architectural proposal, technical architecture. This is the typical way, like we discussed it in these blocks. Diagrams. So you should find out and select the components to build up the Lambda architecture. So you have the database, you have the serving layer, you have the batch layer, you have the user interface, and so on. And you choose components or also cloud services, which are open source based. Yeah? So that in principle, at any time, you don't have a vendor login. And then you can decide how you run them. But you should argue, yeah. You should give reason why. Yeah? So why did you do it like that and not others? Now that's the important thing. That means you should check your selections against the requirements and could argue from the requirements. Yeah? So that is the idea. Yeah? And so the result would be presentation, including the architectural picture and explanations, reasons, and so on. So that's the goal. And I hope that so it's for now, we do it now. So I just discussed it, but maybe you can ask now if since I wrote it in front of you, if this is clear, yeah? Or if there are any understanding questions on the task, if it's clear what you need to do. So maybe to make it even more precise, what do you need to do? search for candidates each component that you need. Like, for example, of course, in alignment with the requirements that I met. So it must be open source, it must be blah, blah, blah. Yeah? And then maybe before you do that, you should that's the typical process how you derive an architecture. You first of all determine what you need, then you find out what are your choices, what can you use, principle, and then you have to compare and select according to the requirements, and then sum it up in a diagram, an architectural diagram, and in your presentation. Yeah? So I hope this is clear. I hope. If not, please ask. So that's the exercise that I put here. Yeah? And it combines what I just taught you on about Lambda and Kappa architecture, and together with the things that we discussed last week in the video that I gave you, the cloud computing fundamentals. So what is AIS and so on? What are the advantages there? And yeah, so we'll do that as a group work now, and we have a lot of time for that now. 2 hours, not exactly 1.5 hours. But anyway, so we will start with that, and we do it in a virtual session, breakout session. But this time we will use random groups to make it more fun. And also, I think not all of you are here, so it doesn't make sense to have these standard groups, but we will, and we also did not make groups anyway, so let's do. And I want you, of course, so we have about 34 people. So maybe let's have groups between 3 and 4 people to make it a bit more interesting. Smaller groups, more interaction. And I'm looking forward to the result. When you're finished, please upload your presentation here to the exercise in the course. Okay, that's so we can present them and discuss them. Okay, once more, any questions? Is the task clear? Okay, I created 8 groups with 3 to 4 people. And the goal, of course, is that you now try to work together and find a solution to this question. All right, so let's start. And if there are no more questions. All right, so if not, I hope that the task is clear for everyone. And we start. I send you to the breakout sessions now, and look what happens.
Hallo Herr Brune, ich bin noch
Yes.
mal kurz rausgegangen. Könnten Sie mich noch mal bitte schnell in der Gruppe hinzufügen? Danke sehr.
Moment, wir sind raus. Okay, so welcome back from the breakout sessions. Thanks a lot for contributing, working. I've seen some intermediate results, which looked already quite good. So I invite everyone to upload those of each group who have kind of the final version of the document. Please upload it here in our exercise. So next week we could start with some presentations of your results and discussions about that. And the things that I've seen so far look quite, let's say, natural or straightforward. So most of you choose the same components, which is okay because it's kind of these are kind of the mainstream solution for the problem, which is good, and which we also will cover in during this course then. Yes, so that's fine. Okay, so maybe let's see if there are now some more uploads. Yeah, one more. So, but there could be some more, I guess. So please. Yeah, 3, perfect. Okay, so obviously at the moment we have 3, but maybe use the remaining time to finish that. Okay, so that's it for today. Thanks a lot for participating, and yeah, so I think you all had now the chance to think about cloud and also the Lambda architecture, which is important. And I hope that this exercise helped to make it a bit more understandable. And 5, cool. Score is going up. So next week, we will start then with presentation of your results. So every group can think who wants to present. And yeah, so that we get an overview. I think the answers could be similar, but maybe the arguments are not, or the reasons you give are not always all the same. So it might be interesting to have a look at different results as well. One hint, I uploaded the videos of last week and also from this morning already, so you can use them to watch again, recap the results of the work of last week. Okay, so that's it for today. If there are no more questions, I will stop the sharing and also the recording then, and we will meet again next Tuesday.
Thank you, Professor. Have a nice day.
Have a nice evening. Thank you. Bye-bye.
Thank you, everyone.
Thank you. Bye.
Thank you.